What is liquid to liquid extraction?
Okay, liquid to liquid extraction is you're given two solvents, one with the desired solute in which you want to extract, and you use another solvent in which it has properties closer to that given solute in order for you to use that extraction solvent to extract the given solute from the solvent in which it was dissolved.
Is benzoic acid soluble in both water and methylene chloride?
It is. It's soluble in both solvents.
Why is it soluble in both water and methylene chloride?
It's soluble in water because benzoic acid has a polar part to it, which is the top part you see there, but it also has a non-polar part, which is the benzene ring, and that is what's attracted to methylene chloride. And methylene chloride is overall more non-polar, which allows benzoic acid to also be soluble in methylene chloride.
Okay, so will it be more soluble in one than in the other?
It actually will. Benzoic acid will be more soluble in methylene chloride because of methylene chloride's structure. Methylene chloride overall, as I said, is more nonpolar. It does have a small polar component, which is the hydrogen part, but it's overall, because of the chlorines, it's overall more nonpolar. Therefore, benzoic acid, the part of benzoic acid which is more nonpolar, is more soluble or attracted to methylene chloride, as opposed to the smaller region of benzoic acid, which is polar, which is soluble in water. Okay, my turn to ask you a question. What's the difference between single extraction and multiple extraction?
Single extraction involves using one single volume of extraction solvent and adding it to the solution, to the solute solution, and which is in this experiment was benzoic acid solution. And multiple extraction involves using the same amount of extraction solvent, but in different portions, and it all depends on the amount of multiple extractions you want to do. So if you want to do 2 extractions, you divide the volume by 2 and use those 2 different portions to apply it to the solute solution. And if you want to do it with 3, you want to do 3 extractions, then you divide the volume by 3.
Which is more efficient?
Multiple extraction is more efficient.
How do you know?
Based on the experimental results, we concluded that multiple extraction was more efficient because there was less benzoic acid in the aqueous layer of the multiple extractions than there was in the single extractions based on the titration.
Okay, and that makes sense because when you do multiple extractions, you're allowing the methylene chloride, which is the extraction solvent, to come into contact more with the aqueous layer, providing a higher probability that methylene chloride will interact with the aqueous layer and more of a chance for it to extract the benzoic acid.
Here's an illustration of the separatory funnel. This is the aqueous layer, and this was the extraction solvent.
Okay, I get it. So the methylene chloride, which is the blue, where the blue arrow is pointing, doesn't mix, and from what we explained earlier, won't mix with the polar water layer, which is the aqueous layer containing the benzoic acid. So what is KD?
KD is the distribution constant.
And what is the expression for that?
KD
or how do you calculate
equals the concentration of the organic layer over the concentration of the aqueous layer.
Okay, and do you know its usefulness?
Well, I know it helps us determine if the reaction will favor the products over the reactants. But what do you know about the KD?
I know that it's a ratio. It's a ratio, like you said, it's the ratio of the concentration of the organic layer over the concentration of the aqueous layer. But also, it gives you a constant value that will be that constant value at a certain temperature. So, as we perform the extraction at room temperature, the solute or benzoic acid will be distributed through those two layers at a particular ratio.
Hence the KD, which is the distribution constant.
Okay, so for the single extraction and the multiple extraction, how did you determine the amount of benzoic acid extracted from the aqueous benzoic acid solution?
Well, we determined the amount extracted of benzoic acid using the aqueous layer that was left behind after the extracted solvent was taken out.
And is the aqueous layer the one in this Erlenmeyer flask here?
Yes, that's the aqueous layer. We added a phenolphthalein indicator, and then we added NaOH solution using the titration apparatus.
So in this titration apparatus, the one that this arrow is pointing to, you had base in there, which was sodium hydroxide, right?
Yes, and we added it slowly until the phenolphthalein indicated that the aqueous layer solution was neutralized, and we determined how much benzoic acid remained in there, which allowed us to determine how much benzoic acid was extracted in the organic layer, which is what wasn't in the aqueous layer.
Okay, so let me get this straight. So you titrated with base, and you used base because we had acid here where this red arrow is pointing. We had acid in the aqueous layer.
Some acid remained in the aqueous layer because of the difference in polarities, which we discussed.
Okay, so there was some acid here in the flask, and so we titrated that, and
to determine how much base was necessary to neutralize the acid that remained in the aqueous layer. And then we subtracted the amount. We determined the amount that was
in the organic
benzoic
layer
acid in the aqueous layer, and then we subtracted that from our initial amount to determine how much was extracted in the organic layer.
Okay, I think I get it now. Extraction kind of seems kind of fun.